Hello, ladies and gentlemen. Moving on to another lesson this week. Hope everybody's well. We've had a beautiful weekend, lots of sunshine. So today our lesson is on interpreting functions. So basically we're interpreting graphs. Okay, now I want us to go back and remember that we have independent variables, and the independent variables are on the x-axis. So remember, the x-axis is the horizontal that's going to go left and right, so at the bottom of the graph. And then we have dependent variables, which are on the y-axis, and the dependent variables, they go up and down like that. Okay, so the y value depends on the x value. So this is the one running the show. This is the one controlling what's happening on the graph. Okay, the independent variables. Now, when drawing and interpreting graphs, there are two basic types, okay? And of those two types, there's one we call qualitative. Qualitative graphs just have a general idea. They're looking at how the information kind of, or there's a trend in the information, I guess we should say. Okay, you won't see numbers there. It just has what the independent and the dependent axes, what they represent, and what's happening as you move along the independent. How is the dependent moving? In a quantitative graph, you should think about this one, quantity, right? So in a quantitative graph, it has numbers or data that can be measured or counted. Okay, now they basically are showing information and how it's related to each other, but in a quantitative graph, you're going to find the axes have numbers. In a qualitative, we're just seeing the general trend. Is it moving to the left or to the right, up or down? Okay, so we're going to go through a few examples. The first example is a quantitative graph, right? So this one is going to have numbers, right, on the axis. So this is a graph that shows the amount of gasoline in a tank of a salesperson's car at different times of the day. So now when we think about these two pieces of information, is the amount of gasoline in the tank going to be driving this, or will the time of day be driving the information? So thinking about this, does the amount of gas in the tank depend on the time, or does the time depend on the amount of gas? Well, the amount of gas depends on the time. The time is down here. This is the independent variable. And the time of day will depend or will determine the amount of gas. Okay, so this one is the dependent. So the more time that the salesman drives, the more amount of gas is going to be used, or the amount of gas in the car is going to drop in the gas tank. So really, we want to describe how this salesperson might have spent their day by just looking at the graph. Okay, so the first thing we want to do is to think about these points here. Okay, so the start of the day is here, and you can see there's a half a tank. And that start of the day for this salesman is at 8. So the salesman is going to start with a half a tank of gas at 8 o'clock, and then he or she is going to drive till 9 o'clock. So from 8 to 9, right, that is 1 hour of driving. You can see that the gas is dropping from a half a tank to somewhere closer to a quarter of a tank, so just above a quarter of a tank. Okay, so this person must be driving because the gas is dropping, right? And then what happens? From the next stage, from 9 o'clock to 10 o'clock, there's the next phase. So from 9 to 10, again, in a 1 hour period, the car must be stopped because there is no gas that is being consumed at all. So the car has stopped. Okay, whoops. The car has stopped for probably a sales call, because this is a salesperson, right? So he's making a sales call. He's spending his time from 9 to 10, that hour, maybe trying to sell something to a customer. The next stage goes from 10 to 11. So between 10 and 11, again, there's 1 hour, and you can see the gas is dropping. Now, in that hour, it doesn't seem to drop quite as much as the first hour, right? Remember, slope, okay? This is a negative slope, okay? This is a zero slope, and this one is also a negative slope. Now, it's not quite as negative as the first one. He is going to be driving, but he must be driving slower because there's less gas being used up. And then you can see that there is, again, between the next time frame from 11 to 12, there's another hour that goes by, and it's got back to a zero slope. Okay, and on that zero slope, the car again must be stopped for a sales call. And then what we see is a little bit of a drop there from about 12, this is 12:30, so they're driven maybe for 15 minutes. So somewhere between 12 and 12:15, right? That's a 15-minute drive. And then the car has all of a sudden had the gas jump up. So what do you think has happened? Likely, this salesperson has taken that 15 minutes to drive to a gas station. And at that gas station, all of a sudden at 12:15, okay, the gasoline has shot up all the way up to a full tank, okay? And then there's another 15 minutes approximately that happens here. So drops and then rises, and then there's a little bit of a drop again. So at 12:15, the salesperson is going to fill with gas. And then from about 12:15 to about 12:30, the gas drops again a little bit there. So they are going to drive maybe to have lunch, because think about the time frame. We're now at like 1 o'clock. So maybe they're going to drive for lunch, okay? And then from 12:30 to 1:30, right? 1,300 hours is 1 o'clock to 1:30. So from, what time was that again? It was 12:30 to 1,300 hours, or sorry, 13:30. 13:30, that's again 1 hour. This is where they're going to have lunch. Maybe they drove back to the office. Maybe they drove to a restaurant. We don't really know, but this is where we're stopped. And we can assume just because of the time of day that they're probably having lunch. Maybe they're having a business lunch. They're trying to sell over the lunch hour as well. All right, and then the car again has time going by and the fuel is dropping. So now from a 1:30 till about 14:15. So maybe from 13:30 to 1415, so that would be about 2:15. The car is going to drive again. Okay, you can see it's stopping again at this spot. And now from that 14:15 till what, 4 o'clock or 1600 hours, the car has stopped. And maybe the business person has gone for another meeting, okay, and maybe gone for another sales call and trying to sell whatever product he or she has. And then lastly, there's another section here from 1600 to 1700. And again, that's an hour that has gone by where they have probably driven back to the office, right? And that's the end of the day. The car is parked there and it's not going to be moving again. Okay, so that's kind of a look at what's going on. It's the time of day that's driving the amount of gas, right? You can see definitely after 1700, there's no activity in the car because the time of day is the end of the day and the car is not being driven. Okay, now we need to go back and remind us on what is our domain and range. So remember, domain is the X values and the range is the Y values, okay? So our X is going left and right. So remember, our X in this case is going to be at the highest, which is 1700 hours. So it's going to be lower than, less than or equal to 1700 hours. And it's going to be higher than the lowest value, which is 800 hours. Okay. Now, our range is our Y values, and so the highest value we have for our Ys is going to be a full tank, so it could be equal to a full tank or less than, and then they never get any lower than halfway between empty and a quarter. That would be 1/8 of a tank, okay? So it's going to be greater than or equal to 1/8 of a tank. Okay, now I started to talk about slope. So negative going down, 0 as horizontal, negative going down, 0. When it goes straight up and down like this is undefined. Remember? And then we've got a little bit of, again, a negative, and this is a 0, and this is a negative, and this is a 0. And then this is a negative. Notice that there are no, in fact, positive slopes on this graph. Okay? Let's move on to a qualitative graph. So on a qualitative graph, remember there's going to be no numbers, right? We're just looking at the general, general trend. Okay, so we've got a graph here, or in fact there's two graphs, and those two graphs are going to describe two pleasure boats, and we want to be able to compare the boats by age, by cost, by speed, and by length. So we're going to compare the two boats. So we can see there is boat A and B. Okay, so the cost and the age is on one of the graphs. So the age of the boat, remember this is the independent. And this one is the dependent. So how old the boat is will determine the cost. That's the independent. The older the boat should be the lower the cost, right? The newer the boat should be a higher cost. Now then let's maybe look at writing this down. So we'll start with age. Okay, so if we're looking at the age of the boat here, boat A is older than boat B, okay? Because as we go along in age, we can see B is farther down the age than A is. So for A, B is older than A. The next thing we want to do is we want to look at cost. Okay, so now looking at cost increases as we go up. Here's where A is in cost, and there's where B is. So A is going to cost more than B. Oops. A is going to cost more than B. The next thing we want to look at is speed. So again, speed is the dependent variable and length is the independent variable. So the length of the boat will determine how fast it goes, possibly. Okay, so let's see speed. Okay, so let's look at this. So speed is going up, and we will see that B is in fact higher than A. So the speed of B is going to be higher than the speed of A. So B is faster than A. And lastly is length. Okay. Now, when we look at this, the length of A and B are the same. Okay, so for length, A and B are the same. So what we can get from this, in fact, is that length doesn't determine speed, right? Something else must determine speed because the length is the same, but the speed has not changed. Okay, or I mean the length has not changed, but the speed has. In the first graph, we can see that the older the boat is, the less the cost is going to be. The younger the boat is, the higher the cost is going to be. So there is a relationship here where age is going to affect cost. In this case, length does not determine speed. Okay, so that's what we can get from this graph. Okay, our third graph here is going to be a graph that shows the distance versus the time. And usually when we have the something versus something, okay, the dependent one goes first versus the independent second, okay? So here's our graph. This one, time is independent and distance is dependent on time. Okay, so we want to, in fact, look at the graph of distance versus time for a car traveling from Fredericton to Moncton. We want, again, describe what's happening between points A and B, B and C, C and D, C and D, and D and E. And we're going to give the speed at each stage, and we need to determine if this is a qualitative or a quantitative graph. So looking at this, remember that qualitative just has the general trend, and quantitative, you need to think about quantity, and this is going to have numbers. So when we look at this graph, there's a time with numbers here and there's a distance with numbers here. So this is definitely a quantitative graph. Okay. So now let's describe what's happening. Okay, so from A to B, how much time has gone by? 1 hour has gone by. As we go up, we end up going from 0 to 1 hour. and then we end up actually going up from 0 to 100 kilometers. So from A to B, the car travels 1 hour and 100 kilometers. Now to figure out the speed, we just take the kilometers and divide it by the hours. So 100 kilometers divided by 1 hour is going to equal 100 kilometers per hour. Okay, let's go to stage B and C. So what's happening here? So from B to C, we're going from hour 1 to hour 2, and we're still at 100 kilometers. So the car has not traveled anywhere for an hour. So between B and C, it says the car has not traveled for 1 hour. Okay, so then that means that we've got 0 kilometers in 1 hour. So 0 divided by an hour is going to have a speed of 0 kilometers per hour. Okay, let's go to C and D. So going to C and D, what do we see? We're gone from hour 2 to hour 3. And we've gone from 100 to 150. So it's gone up 50 kilometers in 1 hour. Okay, so this car has traveled for 1 hour and it's gone 50 kilometers. So to figure out your speed, it's going to be 50 kilometers divided by the 1 hour is going to equal 50 kilometers per hour. So the first hour was probably on a freeway, somewhere where they can go pretty fast. Then it seems to me that they've stopped for a little bit of a shop or maybe for lunch, and then they're traveling again for 1 hour, but at a much slower pace. So maybe they're now on a secondary road or country road where they can't be traveling as fast. Okay, let's look at D to E. Okay, so now from D to E, they're going from hour 3 to 4 to 5. So that's gone 2 hours now. And how much have they traveled? They've traveled from 150 to 200 kilometers. So the amount that they've gone up has been only 50 kilometers, okay? So the car has traveled 2 hours, and in those 2 hours, they have only gone 50 kilometers, okay? So now this is the slowest yet, right? They did 100 kilometers in an hour. Well, if we don't include the zeros, but in the actual driving. And then they moved 50 kilometers, half that speed. And now they've taken that 50 kilometers and it's taken them 2 hours. So let's work out the speed. So we're going to take 50 kilometers. We're going to divide it by 2 hours. 50 divided by 2 is going to give us 25 kilometers per hour. So now they're traveling quite slow. So either this is some kind of a construction zone, or maybe it is gridlock. There's some kind of an accident on the freeway and they've really had to slow down. So we can actually determine things like speed from graphs that have got numbers or quantitative graphs, okay? Okay, let's move on to a fourth example. Okay. In the fourth example, you are the first person to get on and off of a Ferris wheel with 5 cars. I've taken a picture here of the Ferris wheel, and you can see 1, 2, 3, 4, 5 cars. And what will happen is the car will stop at the very bottom here, and somebody will get in the car, and then it will start to move up, and the other cars will start to move around. And then the next car, this one will move to the middle here at the bottom, and they'll load up. And then it'll keep moving and the next car will go around until it loads all 5 cars. Okay, and once the cars are loaded, the Ferris wheel makes 3 revolutions before letting people off. We want to sketch the graph of height versus time. Now, we don't really have any data here, But we probably could guesstimate that the graph is going to be somewhere starting at 0, and the height of those cars, if there's maybe 2 meters in height each, 2, 4, 6, maybe it's going to be 6 meters off the ground, something like that. Okay? And over time, we don't really know how long that's going to take. Now, what happens? That first car gets to the bottom, and it's a little bit off the ground. It's not right on the ground. So if I were to break this up into that's 6, this would be 3, and then this would be 4 and 5, something like that. And this is then going to be 1 and 2 and 3. So we're just looking at approximations here. So you're going to get in the car, and it's just going to be a bit off the ground, and we're thinking about where the seat is, right? So you're going to sit there, and you're going to start a little bit off the ground. And you're going to get in the car, and then the car is going to go up a little bit in height as it starts to move around, okay? And then it's going to stop. It's going to stop maybe at, I don't know, 1.5 meters off the ground, something like that. And then it's going to stop, and it's going to load the second car. And then the second car, once it's loaded, it's going to go around, and you're going to end up in this position here, right? So you're going to be a little bit higher. And then it's going to stop again, and it's going to fill the third car, okay? So you filled here, and then it's going to move up. And the second car, you're going to move to there. And then the third car, you're going to move to here. And then the fourth car, you're going to go up again, okay? And then what happens is that you're not actually staying up, because now you're starting to come back down, okay? And then they're going to load, so this is the first, the second, the third, the fourth car, and then they're going to load, whoops, time has to be continuing along. Time is going along for all of these things to happen, right? So time's going along, you're going up, then you're not going up as you load the second car. And then you're gonna, time goes along and you're gonna go up, and then we're gonna load the third car, and then you're gonna go up, and then you're gonna start coming back down, and this is where they're gonna load the fourth car, and then they're gonna load the fifth car, and then you're back down to the ground again, right? So it's 5 cars that have been loaded. At the top, you're going to go up and then back down because of the way the cars will circle there. And then we have to do 3 revolutions, right? So what happens as you do 3 revolutions? Well, you go up continuously, and then you come down continuously. Up, whoops, I've gone too far. Okay, let's try this again. We can't go below 0. So, right, this is where the seat of the car is, so we can't go below that. So we're going to go up to the height, the maximum height, which was about here, and then we're going to go back down. There's 1 revolution, 2 revolutions, and 3 revolutions, and then you come back down to your starting point. Okay, it's a slow process loading those cars, and then around, up and down, up and down, up and down, and then there'd be again that process of emptying the cars, okay? We don't have to show that, but the loading and then the 3 revolutions, okay? Now, remember that this is time on the bottom. You're never going to be going backwards in time, so you have to continue with the time going from left to right. Some students think that your graph should look like this because you're making a circle in your cars traveling up. Doesn't matter, you're never going to go backwards in time. Yes, the cars will go backwards, but the time will never go backwards. All right? Okay, couple more. So this 5th example here is, suppose that someone turned on the hot water tap in your house, okay? A hot water tap in your house in the kitchen. And they left it running, okay? Now, I know that in my house, the temperature doesn't start really hot. it starts probably around room temperature. That's the temperature just that the pipes would be behind the wall. And then it needs a few seconds for it to start moving from the hot water tank and then eventually reach the kitchen sink, right? And the hottest temperature, in fact, of a household should be somewhere around 50 degrees Celsius, okay? So room temperature is going to be somewhere around 20 degrees, so slightly less than halfway. So it starts out here not at zero because the water coming in from the tap is not going to be at zero, which is basically freezing temperature, right? That's a temperature at which water would freeze to ice. So it's not going to start there. So what'll happen? It'll take a minute or so for the water to warm up and to move up to 50 degrees, okay? And then it's going to travel along at 50 degrees for quite a long time, right? And then eventually what happens? My hot water tank starts to run out of hot water and the temperature starts to cool down, right? You probably all had to try and have a shower after 2 or 3 members of your household has had a shower and there's no hot water left, right? So it starts to cool down, and then eventually it doesn't get any colder. It just stays at room temperature, or in fact, it'll stay maybe at that, and then, or it can cool down to maybe groundwater temperature, maybe if I erase that, and it goes down to a little bit colder. It can get colder if you let it run, that's true. You want a cold glass of water, but it's never going to go to freezing. It might go down to, I don't know, maybe around 10 degrees, which is temperature of groundwater. So it starts to drop off to about that 10 degrees, and then it's never going to get any colder than that. Okay, so it might take a minute or two to get that hot water coming. Then you're going to continue with hot water until the hot water tank runs out. Then it'll slowly get colder and colder until you get maybe to groundwater temperature. Okay, that's what it's going to look like over time. Now notice we don't have any time frame in here, so this is a qualitative, not a quantitative graph, okay? Because we're not actually graphing data with numbers. Now the last one here is we want to sketch the graph with the number of minutes of daylight, okay, versus the month. Now most of you should remember that the months, we might go, the beginning month is January, the last month is December. In the middle of that we're going to have it won't quite be in the middle, but we'll go January, February, March, April, May, June, July, August, September, October, November. So the amount of daylight is going to be the dependent on which month you are, right? The daylight doesn't tell you which month. It's the month that tells how much daylight it's going to be. Okay, so that's the driving force here. Now, the longest day of the year is in June. Okay, so here in June, we're going to have the highest. And then, in fact, in December, we have the lowest. Now, here in sort of the area that we're in Pitt Meadows, the longest day of the year might be from 5 o'clock in the morning, the sun rises, to 9:30 at night. And that's maybe around 16 hours. And the lowest daylight is going to be maybe 8 o'clock in the morning to 4:30, something like that. We're going to be around 8 hours. So that's about half of that. Okay, that's going to be our December time. Okay, so the general trend would be for as we go from June to December, right, the days start getting shorter. And as we come from December to January, right, our days are getting longer. So we're going to have a general trend of a graph like this. As we start the new year, the days are longer and longer until we get to the longest day of the year in June, and then they start getting shorter again until we get back to the end of the year. So that's going to be the general trend. Again, this is going to be a qualitative graph, not a quantitative graph. We don't really have numbers in there. Yes, I put sort of rough ideas, but we haven't got data that we're actually plotting exact points. All right, so you're going to have to interpret some graphs. The assignments are going to look long, but the first One is just multiple choice. The second is matching. It's the third one that's going to take a little bit more time. All right, ladies and gentlemen, take care.